Yeah, not sure, so. Okay. He'll just have to bring it, yeah. Okay. Sounds good. All right, bye. We're welcome anytime. I'm gonna have to go right in a second. I'm not here, right? You have 10 minutes to get started?
Yeah, I can just do it over there.
I need a few minutes anyway.
All right, the Bronsted-Lowry acids and bases, we're going to talk about those, and strong and weak acids and bases. So, let's first of all talk about traditional acids and bases. Traditional acids and bases. A traditional acid, basically we go with produces the H plus or the H3O plus ion in water. The traditional base, very similar, only we're talking about produces a hydroxide ion in water. All right, so we're looking for the base. For the acid, we're looking for the H plus or H3O plus. For a base, we're looking for the OH minus. And that's kind of a good starting point for acids and bases. But now we're going to talk about the Bronsted-Lowry theory, which is more encompassing. Bronsted-Lowry acids and bases. Okay, according to the Bronsted-Lowry theory, an acid is a proton donor. And a proton is just a hydrogen ion, an H plus. So really, you're talking about donating a H plus, or a hydrogen ion. A Bronsted-Lowry base is a proton acceptor. So it is accepting a hydrogen ion. So that's the difference between a Bronsted-Lowry acid and base. So let's look at a couple examples here. So let's start with HCl plus water. And when we do that, we're going to end up with H3O plus or H plus, remember they mean the same thing, plus Cl minus. Okay? Well, HCl is donating the hydrogen, therefore it is a Bronsted-Lowry acid. H2O is accepting the hydrogen, therefore it is a base. And then Cl minus, or HCl, gave up the acid, and what remains is Cl minus. So this would be what's called the conjugate base. And H3O plus would be the conjugate acid. So we would say HCl and Cl minus are a conjugate acid-base pair. And likewise, H2O and H3O plus, or H plus if you'd rather, are also a conjugate acid-base pair. And you might want to say base-acid pair, but it doesn't make any difference. They're considered the same. All right, let's do another example. Let's say we have ammonia, NH3. And we're going to use water again as our reactant, or the reactants. And the products of that are going to be NH4 plus OH minus. So since we have an OH minus, we know that we have a base for sure present here. Well, in this case, H2O gives up a hydrogen. Therefore, it is the Bronsted-Lowry acid. So it donates the hydrogen or donates the proton. Ammonia accepts the proton, therefore it is the Bronsted-Lowry base. Okay, well, NH3 becomes NH4 plus, and NH3 is the base, therefore NH4 plus would be the conjugate acid, and OH minus then would be the conjugate base. So NH3 and NH4 are a conjugate acid-base pair. And our other conjugate acid-base pair would be H2O and OH minus. So, base, conjugate acid, acid, conjugate base. Now, if you'll note, in the first situation, water acted as a base. In the second reaction, it acted as an acid. So you can see that water isn't always an acid, isn't always a base, and that's why the Bronsted-Lowry theory is nice. Let's do one more. CH3OH, this is methanol. We're going to use water again, just because it's easy. And we're going to get H3O plus CH3O minus. Okay, who is giving up the hydrogen? Well, the methanol is giving up the hydrogen to the water. Therefore, the methanol, or the CH3OH, is the acid. H2O is the base. H3O plus is the conjugate acid. CH3O minus would be the conjugate base. So our acid-base pair is CH3OH is the acid, and CH3O minus is the conjugate base, and our base is H2O, and our conjugate acid is H3O plus. So that's how the definition of a conjugate acid base in the Bronsted-Lowry definition. Hydrogen donor is the acid, the proton or hydrogen donor or proton donor is the acid, the proton acceptor is the base. All right, so that's it for Bronsted-Lowry. Now let's talk about weak acids, bases, strong acids and bases. We're going to start with strong acids. So first of all, the definition of a strong acid is it ionizes 100% in water. So HCl, hydrochloric acid, is a strong acid, and it goes 100% in the direction of H plus Cl minus. We get nothing, everything. So if I started out with 1 molar of this, I would end up with, and then I had none of this initially. So initial, I would end up with none of this because all of it gets used up. So we would lose 1.0 and we would end up with 0. And we would gain 1.0 of this because it's a 1-to-1 ratio, and we would end up with 1 of this and 1 of that. The Cl minus. So 100% of it ionizes 100%. Okay, examples of strong acids. Okay, hydrogen, and they're always going to contain hydrogen. So hydrogen with column 7A's other than fluorine. So HCl, HI, HBr. Those are all called binary acids because they're hydrogen and one other element. Okay? All other binaries, acids, would be weak. So those are the strong binary acids. They ionize 100%. H2S, H2SE, HF. These would be weak binary acids. And by being weak acids do not ionize 100% in water. Okay, so strong binary acids, HCl, HI, and HBr. All others are weak. They do not ionize 100% in water. Okay, all other binaries. Now let's talk about other types of acids, oxyacids. Oxyacids are going to contain hydrogen, oxygen, and one other element. Now, if you look at your ion sheet, it's going to be things like H2CO3, HClO, HClO2. Okay? Those are examples of oxyacids. They have hydrogen, oxygen, and one other element. So here's how we tell if they are strong or weak. If there are two or more, let me write a couple more examples here, HNO3, H2SO4, HClO3, HClO4. Okay, here we have 3 oxygens and 1 hydrogen. Okay, if we have 2 or more oxygens and hydrogens, it's strong. Here we have 3 oxygens and 2 hydrogens. Let's try that again. Yeah, 3 oxygens and 2 hydrogens. Difference of 1. Therefore, that's a weak acid. H2SO4, 4 oxygens, 2 hydrogens, difference of 2. So that would be a strong acid. Here, 1 hydrogen. Let's do it with the 1 oxygen. We got 1 oxygen, 1 hydrogen. Difference of 0, so that's definitely a weak acid. Here, 2 oxygens, 1 hydrogen, difference of 1, weak acid. Here, 3 oxygens, 1 hydrogen, difference of 2, strong. Here, 4 oxygens, 1 hydrogen, difference of 3, strong acid. So for the oxyacids, strong oxyacids contain 2 or more oxygen atoms than hydrogen atoms. All other oxyacids are weak. And just like before, if it's strong, it has to ionize 100%. So if I have HNO3, strong acid, okay, when I put it in water, I get 100% of H plus and NO3 minus. Where if I have a weak acid like, let's say, H2CO3 is a weak acid, it's in equilibrium, which means I get a little bit of this H plus and HCO3 minus, but I have a lot of this. So very little of this, and we still have, at the end, we have mostly this. Okay? All right. So, at weak bases and acids. I'm sorry. Let's talk about strong and weak bases. Strong base, same rule applies. Ionize 100% in water. Weak base does not ionize 100% in water. So again, if I have a strong base like ammonium hydroxide, and for right now we're going to identify bases as primarily having hydroxides in them. 100% is going to go to Na plus OH minus. So at the end, I have none of this left and all of this, 100% of the stuff over here. Okay, how do I identify a strong acid and base? Okay, off your periodic table, any column 1, 1A, hydroxide, is a strong base. So you look at column 1 in your periodic table, lithium hydroxide, sodium hydroxide. So sodium's a column 1A, lithium's a column 1A. Potassium's a column 1A, hydroxide, strong. Rubidium, column 1A, hydroxide, strong. Cesium hydroxide, CSOH. Cesium's a column 1. And the last one is francium hydroxide. Column 1A hydroxides, they're all strong bases, they ionize 100%. Likewise, column 2A hydroxides are strong bases. So, BeOH2, beryllium's a column 2A, so that's a strong base. Magnesium, column 2, those would be a strong base. Magnesium hydroxide. Calcium hydroxide, strong base. Strontium hydroxide, strontium's a column 2A, strong base. Barium hydroxide, column 2A, so it's a strong base. And radium hydroxide, RaOH2, strong base. So column 1A or 2A hydroxide are strong bases. All other bases are weak. So if I had something, well, let's just do a couple examples here of strong or weak acids first. Let's do HClO, H2SO4, H2SO3, HF, HBr, and let's see, what should we do? HBrO2. Okay. First of all, these are the binaries. Binaries, the three strong binaries are HCl, HBr, and HI. So binary means hydrogen and one other element. So binary. HF is not one of our strong binaries, so that's a weak acid. HBr is one of our strong, so strong acid. Okay, for our oxyacids, we're comparing hydrogens and oxygens. So we got 1 and 1. Difference is 0, so it has to be 2 or more. So that's a weak acid. Here we have 4 and 2. That's the difference. We have 2 more oxygens and hydrogens, strong acid. Don't know why I did H2SO4 twice. Let's try H2SO3. 3 oxygens, 2 hydrogens, difference of 1, weak acid. HBrO2, 2 oxygens, 1 hydrogen, difference of 1, weak acid. Let's do one more, HClO3. 3, 1, difference of 2, strong acid. Okay. Weak acid or strong. Let's do that again. Weak base or strong base. All right, barium hydroxide, BaOH2. Zinc hydroxide. Lithium hydroxide and copper hydroxide, CuOH2. Barium, if you look up the periodic tables, a column 2A, strong base. Zinc, not a column 1A or 2A, weak base. Lithium, column 1A. Hydroxide, therefore it's a strong base. Copper is in the middle, transition element, not a column 1A or 2A, so it's a weak base. All right, I want to talk about one more thing on naming acids. Okay, if we have a binary acid, which is hydrogen and one other element, when we name them, it's just hydro, some form of the element, that's the negative ion, and it ends in ic. So we got HCl, HBr, HI, H2S, H2SE. We'll just use those as example. Hydro, chlorine, and it just goes chloric. Hydrobromic. Hydroiodic. S is sulfur, hydrosulfuric. And H2SE, hydroselenic. The only time you use hydro is when you have these binaries. Okay, that's pretty simple. Now, how about the oxyacids? Well, you have to look at the negative ion. So let's say we have H2SO4. That would be hydrogen with a sulfate. when we name these, we look at the negative ion. The negative polyatomic ion. So we have sulfate. So basically the 8 becomes ic. So this would be called sulfuric. Now if you put sulfic, that would be okay. Okay, H2CO3. This is hydrogen with carbonate, hydrogen carbonate. So the acid name is carbonic acid. So 8 goes to ic. Naming oxyacids. 8 goes to ic. Let's do one more. NO3, hydrogen nitrate. So this would just be nitric acid. All right. Now, what about the other ones? Let's say we have something like H2SO3. This would be hydrogen with sulfite. Now, in this case, ite, the ending is ite, it goes to us. So this would be sulfurous acid. HNO2, hydrogen nitrite. So this would be nitrous acid. So the best example I can give you of this is, let's say I have HClO, HClO2, HClO3, and HClO4. This would be hydrogen with hypochlorite ion. So the acid would be hypochlorous acid. This would be hydrogen chlorite, and the name would be chlorous acid. Hydrogen chlorate. Now 8 becomes ic, so this would be chloric acid. And HClO4 would be hydrogen with a perchlorate ion. So again, 8 goes to ic, perchlorate, spell it right, perchloric acid. So 8 goes to ic, 8 to ic, ite goes to us. Ite goes to us. So that's the way you name your acids. Now, if you also notice, let's just look at this. This one would be a HClO, difference of, if we're figuring out strong or weak, this one would be a weak acid. 2 to 1, weak acid, only a difference of 1. Here we have 3 to 1, difference of 2, so this would be a strong acid. And 4 to 1, difference of 3 more oxygens, and this would be a strong acid. So there's some stuff on Bronsted-Lowry acid and base, what the definition of a strong and weak acid are, determining how we can find which strong acid, which is a strong base, and which bases are weak and which are strong, and also a little bit of naming on acids. Thanks, have a great day.